So let me start with why we are all here. It's of course the problems of current peptide production. As you all know, it requires immense amount of organic solvents, which leads to environmental implications. Also, there are regulatory restrictions, as Karin already told you. DMF is classified as substance of very high concern by the REACH regulation, and the EU Commission has decided to restrict its use from December next year. Altogether, this leads to very high production costs. So, for instance, the global annual demand of pharmaceutical peptides, only pharmaceutical peptides included, is about 1.8 tons. To produce 1.8 tons of, for instance, 27 amino acid long peptide, which is the average length of a pharmaceutical peptide, it requires at least 50,000 tons of DMF or other organic solvents. And for the purification, additional 25,000 tons. This is reflected also in the cost split of the raw materials, where solvents alone make over 80% of the costs. All these problems are well known and were summarized in a recently published paper from the ACS Green Chemistry Institute Pharmaceutical Roundtable, where all big pharma companies are members. They also publish the demands they have for a greener peptide synthesis. So to address these problems, several approaches were published and developed. For instance, in 2009, the solid phase peptide approach in water was published using microwave-assisted heating. However, this is of course not scalable and of course too energy consuming. The Hoyo et al. Published an approach with water dispersible FMOC or Bock protected amino acid nanoparticles, also using microwave irradiation, but this has the disadvantage that the washing steps still have to be performed with organic solvents. The same working group also published new water-soluble protecting groups shown here, but they all have intrinsic disadvantages. For instance, restricted stability or moderate water solubility. They are all very expensive and complicated to synthesize, and in case of cysteine and methionine, auto-oxidation was observed. The CEM Corporation claimed in a patent application another water-soluble protecting group, the so-called Smoc group, but they dropped the patent because the synthesis of this protecting group is very expensive and has a very complicated deprotection mechanism. Another approach was to use novel surfactants as nanoreactors to synthesize dipeptides in water. But of course, this is also very limited in scalability. Another approach is a solvent-free peptide synthesis using ball mills, which was published in 2009. But this was also limited to rather short peptides. They synthesized 5 moles. A very recent approach is to use water polar clean mixtures. Polar clean is a polar solvent or co-solvent used in agriculture. They were introduced for the circular aqueous peptide synthesis, which worked quite well. There are many other attempts to substitute DMF as solvent with greener organic solvent or solvent alternatives. For instance, there's styrene distributed by Merck as a bio-based alternative, which is derived from cellulose, or Bachem in collaboration with Novo Nordisk investigated binary mixtures of different polar organic solvents, and they use in peptide synthesis. Or Two other publications we found they used the gamma valerolactone and formyl morpholine and propylene carbonate as solvents for peptide synthesis. However, the conversion is often limited by the application of Fmoc amino acid building blocks due to their low solubility. Our approach is based on new water-soluble building blocks, structure you see in the middle, the use of which allows us to substitute organic solvents with water, thereby reducing the amount of hazardous waste. And due to intrinsic fluorescent properties of the molecule, it allows for the first time real-time monitoring of the reaction progress. We have also developed a purification concept and a wastewater treatment option. Altogether, this leads to a reduction of process costs of up to 50%, an efficient use of chemical resources, an eco-friendly, more sustainable process, and of course, solvent-free end products. So let us have a closer look to the Smoc protecting group. It is based on the Fmoc structure. Merrifield introduced in the 70s already the monosulfonated variant for peptide purification purposes, and our Smoc is the desubstituted or the desulfonated variant. The molecule has a unique combination of water solubility and intrinsic fluorescent properties. So there are two different methods for the synthesis of Smoc protected amino acid. The first one is the direct sulfonation of Fmoc protected amino acids, which is in some cases possible. And another variant is to use Smoc chloride and protect the respective amino acid. Here shown is an exemplary HPLC chromatogram of Smoc alanine and the side products which can occur during synthesis. So at 7.8 minutes we have the Smoc alcohol, at 11 minutes we have the Smoc alanine, and there's of course some monosulfonated variants of both. Relevant for peptide synthesis is only the monosulfonated Smoc amino acids, but it reacts equally as the Smoc amino acid, and we did not observe any side reactions with the Smoc alcohol or the monosulfonated alcohol. So then we took a closer look at the Smoc deprotection. We tested different bases in aqueous media, as shown here in the table, and we found that Smoc is more base labeled than Fmoc. So we can reduce the amount of base and therefore reduce the base catalyzed side reactions. Here shown is excitation and emission spectra of Smoc glycine. As we already told you, there are intrinsic fluorescent properties, and as you can see, there's a small Stokes shift, and this would allow for an inline monitoring of the coupling and deprotection step, and an automated decision whether another coupling step is needed. But we did some research with an on-resin monitoring, but of course the solution monitoring would be more preferable. But this needs a bit more work. So now my colleague Sasha will take over and introduce the details of our technology.
So the most important part for peptide synthesis in aqueous systems is, of course, the coupling efficiency of amides in water-based systems. Therefore, we made a series of experiments with a small system with Smoc proline, tyrosine or methyl ester as a model system with various coupling reactions with sodium hydrogen carbonate as a base, and tried different solvent systems. As you can see here, the most efficient coupling system for in situ coupling is EDC Oxima. Pure coupling efficiency in pure water is around 90.7%, which is better than all other systems in comparison. And interestingly, the coupling efficiency is highly increased by adding up to 30% acetonitrile, ethanol, or isopropanol, resulting in coupling efficiency of 99.8%. So it's quite comparable to standard organic synthesis in DMF. So this is basically our adapted SPPS strategy. Of course, it's based on Merrifield's SPPS strategy. We start with a water-compatible resin. There are some commercially available, like Tentagel or Chematrix resins. There are also some other resins available for polar solvents. So the first amino acid is coupled to the resin, followed by an alpha D protection, and then the next activated amino acid is added. And we added an optional capping step with either sulfonated acetic acid, for example, or normal acetic acid. It's depending on the purification strategy that is chosen afterwards. If you use the sulfonated label, we have our correct intermediate and sulfo-labeled side products. And if we repeat the cycle n times till our peptide is synthesized and cleave the peptide from the solid support, we have our target peptide in solution. We have a series of labeled side products in solution, and of course cleaved side chain protecting groups. And if you run this mixture over an ion exchange column, all sulfo-labeled impurities stay on the column, and only the target peptide is able to run through. Of course, it can be done the other way around with conventional capping with acetic acid and putting the last Smoc protecting group on the resin, and so the peptide will stay on the column. This is the way that Merrifield designed its purification method. Here are some examples for peptide synthesis. This is a small peptide that's interesting in the cosmetic industry. It's PyGQPR. This was synthesized on a preloaded HNPB Chematrix resin. And coupling were performed with 2 equivalents of the Smoc amino acids, 4 equivalents of EDC, 2.2 equivalents of Oxima in 20% ethanol, and as base 3.5 equivalents of sodium hydrogen carbonate. Deprotection was performed in 20% ethanolamine for 5 and for 10 minutes. Coupling of the palmitoic acid was performed in higher molar excess. It's necessary to go up to 90% in ethanol because of the low solubility in aqueous media. The purity shown of the crude peptide is here. It's around 86% and confirmed by MS. So the next example is the synthesis of an Smoc heptaarginine. This was done on a Chematrix rig amide resin. The resin was loaded with 3 equivalents of the Smoc amino acid, 5.5 equivalents EDC, 3.5 equivalents Oxima, and 3 equivalents of sodium hydrogen carbonate. Synthesis was done with double coupling steps, or the resin loading, sorry. Coupling was done with the same conditions, but only with single coupling steps in 30% acetonitrile. Deprotection in this case was performed with 1 molar sodium hydroxide, also for 5 and for 10 minutes. The interesting part is that it's possible to use arginine and water-based synthesis without side chain protecting groups, which is removing some of the problems during the organic synthesis of heptaarginine, where after cleavage from solid support, up to 3 PBF protecting groups are still detectable by ECMS. This is an example. We are not allowed to show the sequence, unfortunately. This was a cooperation with a pharma company. It's an octapeptide they used for fragment condensation. It was also performed on a Chematrix ring amide resin. The resin and the coupling were performed under similar conditions with 4 equivalents of the Smoc amino acids, 8 equivalents EDC, 6 equivalents Oxima, and 1.3 equivalents of sodium carbonate as a base. Resin loading was done in a double coupling, normal synthesis in single coupling steps, and deprotection was performed with 1 molar sodium hydroxide again. Shown is a crude HPLC of the peptide synthesized in pure water. Here's a comparison of the organic synthesis performed by the pharma company. Crude yield were about 500 milligrams, HPLC purity were 90.7%, and the racemization of the shown amino acids is quite low in organic synthesis. We did the same synthesis in pure water. Crude yield were about 420 milligrams with 78% purity. Racemization was a bit higher, and the same synthesis in water with 20% acetonitrile is resulting in a nearly the same crude yield and in an HPLC purity of 82% with the same low racemization level in the organic synthesis. The last sample shown here is the synthesis of vasopressin as a more complex peptide. Synthesis was performed on a ring amide K-matrix resin again. All coupling steps are performed as double coupling steps with 3 equivalents amino acid, 5.5 equivalents EDC, 3.5 equivalents oxima, and 3 equivalents sodium hydrogen carbonate as a base. Again, in 30% acetonitrile as double coupling steps. Deprotection was performed with sodium hydroxide again. As you can see on top, this is a crude peptide after cleavage from solid support. Afterwards, followed by an oxidation of the disulfide bridge in aqueous systems. This took around 3 days. Yeah, could be optimized for the oxidation. So here's our recommended procedures for starters for using Smoc technologies. The method 1 is the in situ oxima coupling, shown as before. For starters, for the beginning, before optimization, we would recommend to start with 3 or 4 equivalents of the Smoc amino acids, 5.5 equivalents EDC, 3.5 equivalents oxima, and 3 equivalents of sodium hydrogen carbonate in either 30% isopropanol or acetonitrile, and 45 minutes of coupling time for single coupling, or 2 times 25 minutes with double coupling steps. Washing steps could be performed with simple water. Deprotection could be performed with 1 molar sodium hydroxide. Important is here, if ester side chains are present in the sequence, it's necessary to use other bases like piperazine, for example, or 4-methylpiperidine. Otherwise, sodium hydroxide would cleave the ester side chains as well. Washing after deprotection should also be performed with water. A general recommendation is that ring amide resins needs to be totally dry before cleavage from solid support. Otherwise, there are side reactions that occur. As I said before, recommended resins are Tentagel K-matrix. These are the resins that we use normally. Of course, there are quite a series of other resins available that could be used for polar solvents, but we didn't test all of them, of course. The method 2 we would recommend is NHS ester formation as a pre-activation. This could also be performed with 3 equivalents of the Smoc amino acids, again 5.5 equivalents EDC. In this case, 3.5 equivalents NHS in water. If all of these compounds are diluted in water, the pH should be in the range of 5 to 6. 25 minutes pre-activation time. This could also be monitored by HPLC to see the amount of pre-activation as NHS ester. The coupling is then performed by adding the whole mixture to the amine and adjusting the pH to 8 and readjust over time. If the pH is constant and is not dropping for over 2 minutes, and the reaction is finished. Washing again with water. Deprotection as before. Sodium hydroxide is the easiest one. If ester side chains are present, use an alternative. And washing steps again only with water after deprotection. So the most interesting part, of course, is racemization studies. Most of the people think peptide synthesis in water should result in high racemization levels. We made 2 peptide sequences shown on the top. These were sent to cut tubing for analysis of the racemization levels. As you can see, there's no increased racemization levels detectable in a water-based synthesis. Interestingly, the racemization of cysteine is quite low. It's even lower than in most organic synthesis. The racemization of asparagine or aspartic acid is a bit increased. This could be related to an aspartimide-based racemization process in the synthesis. And of course, this leads us to the more serious side reaction in peptide synthesis, aspartimide formation. As most of you should know, it's based, of course, on asparagine or mainly on aspartic acid in a base catalyzed side reaction, resulting in the cleavage of the side chain protecting groups. This is resulting in a cyclic intermediate, the DL aspartimide formation. And there are two possible reaction ways afterwards: a simple hydrolysis, which would result in an alpha peptide or in a beta peptide. Racemization is also possible for both structures. And if organic bases like piperidine, for example, are used, it's also possible that the two base educts of the alpha and the beta product could occur. To check this aspartimide formation in water, we synthesize the peptide scorpion toxin 3. The sequence is shown here. It's a sequence that is well known to be prone to aspartimide formation due to the motif DG, which is one of the most problematic motifs, of course. We split the synthesized peptides in multiple fractions and incubated them for 3 and for 16 hours in different bases. Shown here is the HPLC of our target peptide. We also synthesized some of the potential side products, the D peptide or the beta peptide as potential side products. As you can see, if we incubate for 3 hours in 1 molar sodium hydroxide, there's clearly a shift to the beta product, and but the target product is still visible. If we use, for example, a weaker base in water, like 5% piperazine in water, there's a minor shift to the beta peptide. In DMF, after 3 hours, there's no observable side reaction. Piperidine, it starts to produce side products, and yeah, after 16 hours, the strong bases, of course, look pretty the same. Interestingly, is piperazine in water, so the level of aspartimide formation increases. It's a higher amount of the beta peptide visible, and with piperidine, interestingly, it's more or less only the base adduct visible, whereas in organic synthesis, the only visible side product is the beta peptide, so it's a completely different mechanism. Interestingly, the observed levels of, yeah, let's say, nearly by piperazine of 1 to 3 or 3 to 1 to the target product here are correlated to formations of aspartimide formation in proteins, which is also called aging of proteins. For example, was observed in literature in the same amount in amyloid beta proteins, for example. So of course, aspartimide formation is temperature dependent. To prove this, we made the same experiment again, only with 5% piperazine in water. We incubated for 3 hours with 3 temperatures at 4 degrees Celsius, at 26 degrees Celsius, and 40 degrees Celsius. And as you can see, of course, the change is clearly visible from the beginning of product ratio of alpha to beta product is 3 to 1. And if you incubate at higher temperatures, the ratio is switched to 1 to 2.5 to the beta product. So aspartimide prone sequences should be synthesized at low temperatures, but this is also true for organic synthesis to reduce the amount of aspartimide formation. And of course, use the weakest possible base. So the last aspect of peptide synthesis, of course, one of the bottlenecks is product purification in the end. There are 3 key drivers for the optimal purification process: productivity, yield, and solvent consumption. And these 3 are linked together, of course. As you can hear in this short graphic, of course, if I want to increase the target yield of the peptide, solvent consumption will go up, resulting in productivity going down. of course. So for many peptides, a target yield of 50% is accepted in terms of solvent consumption in an acceptable amount, but is of course depending on the price of the peptide. Just a short reminder of our purification concept. If we use our capping strategy, or the other way around, we have a target product, a side product, and a clique protecting group. And if we put this on an ion exchange column, either the target peptide runs through and the impurities stay on the column, or the other way around. And this part of purification could be used as either a pre-purification or as part of the multi-column systems to reduce the amount of organic solvents necessary for the HPLC purification. Here are two model experiments to show that this concept works quite well. We did a model experiment. We synthesized hexapeptide 9 in water and did a capping strategy with 2-sulfoacetic acid, shown here. And we coupled all amino acids with 0.95 equivalents compared to Breyer coupling in order to achieve a maximum amount of byproducts. After cleavage from solid support, the crude peptide is shown here. This would be the target peptide. If we run this on an ion exchange column with a pH range of 1 to 3, the target peptide runs through, and nearly all impurities are removed. TFA is still some left in the mixture. The same method also would work in a DMF-based synthesis, of course. We did this in the synthesis with adrenorphine. We did the same experiment, and this time we used 4-sulfobenzoic acid as capping reagent. Did the same experiment. Have a series of side products. After ion exchange, only the target peptide runs through, and most of the impurities stay on the column. As I mentioned before, of course, we can use it the other way around, like Merrifield designed it in the 70s. We do a normal capping strategy with acetic acid or acetic anhydride, similar to the Smoc chemistry capping. The last final Smoc protecting group remains on the peptide sequence. And after cleavage from solid support, the whole mixture is put on an ion exchange column, binds there to the column. And after washing steps, this is a crude example we synthesized. And it's possible to either elute this Smoc protected peptide from the column, depending on the ion exchange material you need under these conditions, or it's possible to do an Smoc deprotection on the column directly and elute only the deprotected target peptide afterwards. So wastewater treatment is of course done in the same way. EDC is a polar coupling reagent. The Smoc protected amino acids are also highly polar and have all ionic groups. So we can remove nearly all impurities in the wastewater via ion exchange columns. Here's an example of wastewater after the synthesis. Of course, Smoc amino acid excess is the best visible impurity. If you run this on an ion exchange column, only purified water runs through. This is also visible by fluorescence measurements, and afterwards it's possible to either regain the amino acids or to put them to waste and reduce the amount of waste, of course. Yeah, then thanks for your attention, and we are looking forward to your questions.